Continuing with from the previous video, this is continuing Chapter 2 in General Biology, some background chemistry. A couple of terms that are important to know, a molecule and a compound. There's some overlap between these terms, but I want you to focus on what's different. A molecule is a term that we use anytime groups of atoms are bonded together. It doesn't matter if they're the same two types of atoms, like we see here oxygen, which is two oxygen atoms bound together, that's a molecule, or water, which is two atoms of hydrogen, one of oxygen, or glucose, C6H12O6, these are all molecules. A compound is a more specific term that means a molecule that has more than one type of element. So notice here you see water and you see glucose, but you don't see oxygen, because oxygen is not considered a compound. It only has one type of atom. It only has two oxygen atoms. Continuing with a couple of other chemistry terminology aspects, chemical reactions are often written with two molecules or compounds on one side of the equation, with an arrow leading to two new compounds or molecules. We call the molecules on the left side of this arrow the reactants, because we are saying these are the molecules, carbon dioxide and water in this case, are reacting to form molecules we see on the right side, which we call the products, glucose and oxygen. Okay, so we're not going to talk too much in biology about balancing these equations, which is a way of putting numbers on the sides here to indicate how many atoms of each or how many molecules of each reactant and how many molecules of product are formed. But if you take a chemistry class, you'll probably learn quite a bit about balancing the equations. Okay, shifting focus just a little bit, I want to talk now about the chemistry of a very important molecule for life, and that's water. Water is a very unique molecule, and if it didn't have the exact chemical properties that it has, life on Earth either would be very, very different or would not exist at all. So in that way, in biology terms, water is the single most important molecule in the universe, really, not just on Earth. We know that all living things are made primarily of water. Cells are made of 70 to 90% water. And I want to go through a couple of the unique properties that water has that make it so special. And as you study, I want you to think about these properties. And as the semester goes on, we're going to be revisiting them quite a bit. So, one of the special things about the water molecule is that here we see a model of water, which is really like HOH is the way that it really exists, not H2O. The oxygen end of a water molecule is slightly negative, and the two hydrogens are slightly positive. That might seem relatively unimportant, except that this creates a weak bond between two sets of water molecules. So here we see the hydrogen end of a water molecule, and this dotted line indicates what's called a hydrogen bond. The hydrogen is weakly attracted to the oxygen of another water. And we see this in a three-dimensional structure. So all the hydrogens are weakly attracted to neighboring oxygens. This weak bond, this hydrogen bond structure, is actually what allows water to be liquid at room temperature. Otherwise, without hydrogen bonds, water would be a gas. We would not have liquid water on this planet, and of course that would mean life is non-existent or very, very different. So these hydrogen bonds allow water to stick together and not float away from one another as easily as most molecules would that are the size of water. So that's item number one, the fact that the structure of the water molecule creates hydrogen bonds. Additionally, this slightly positive and slightly negative portions of the molecule make water a very good solvent. That means that if we mix molecules in water, in pure water, which is actually how most body fluids are, is some mixture of particles in water, water dissolves those particles very well. So we see here, for example, if we add salt to water, sodium chloride, the negative ends of water surround the positive sodium ion. The positive hydrogens surround the negative chloride, and this helps these sodium chloride molecules break down or dissolve. Okay, we see actually some molecules that are hydrophilic. Philic means that they love water. They're very attracted to water and they dissolve very well in water. We do see some molecules like oils, for example, vegetable oil when you cook, or motor oil when we're looking at roads, that are hydrophobic. They hate water. In other words, some molecules actually are not attracted to these negative and positive charges. Um, those molecules do not dissolve in water. So we've got two special features of water. It's hydrogen bonding and its characteristic of being a very good solvent. The fact that water molecules are cohesive and adhesive, meaning that they stick to one another very, very well, makes it much, much easier for water to flow in our bloodstream. You see here an example, blowing up of a bloodstream. The fact that water molecules are stuck to one another, for lack of a better term, means that blood can flow very easily. The same characteristic actually happens in plants. Plants have vessels as well. We don't call it blood, but very similar to blood vessels. The fact that water molecules adhere to each other and actually adhere to some of their surroundings makes the movement of water in plants and animals much easier. Water has a very high surface tension. That means that water molecules like each other much more than water molecules like air, creates what sometimes seems like a skin at the top of water. This prevents water from very easily evaporating and is one of the major reasons why water is found in huge quantities as a liquid on the planet. Water also has a uniquely high heat capacity, meaning it can hold an extraordinary amount of heat before it evaporates. This means that it is a very good reservoir of temperature and energy. That's one of the reasons why keeping our blood at a high temperature allows us to maintain quite a bit of heat, and also why evaporating, when we lose water, we lose heat very, very successfully. The last special thing about water that is so important to life is the fact that unlike almost every other molecule on the planet, solid water, otherwise known as ice, is actually less dense than liquid water. That is extraordinarily unique. We usually think of solids as being much more dense than liquids. But the reason this is important is because rather than when water freezes, if ice was more dense than water, it would sink to the bottom. We know that actually ice stays at the top of lakes and oceans and bodies of water. That means that the water underneath ice stays liquid, and it makes it possible for life to live under the ice. Imagine how different the world would be if ice was actually denser than water, which would mean that basically every time freezing happened, ice would sink to the bottom and would make it impossible for life to be sustained within frozen bodies of water. So here's a summary slide. If I was in your position, I would probably study these properties and be able to describe them and define them and why they're important for life. Last but not least, in our quick little survey of chemistry as it relates to biology, I want to talk about acids and bases. Acids and bases, this whole idea is basically, no pun intended, the discussion of how much hydrogen ion is in a solution. Hydrogen ion is H+, and its most basic, it is a proton. So the number of free protons in a solution is very important to life because protons tend to bind to things and break them down. Water, which we know is hydrogen and an oxygen and a hydrogen, can sometimes break up. These water molecules actually spontaneously break up in solution and give us a hydrogen ion and a hydroxide ion. This happens very infrequently, however. Anything that we call an acid or a base has more or less hydrogen, depending on the word that we're using, more or less hydrogen ions than water. For example, sodium hydroxide, a very, very powerful base, if we add it to water, contributes a sodium ion and a hydroxide ion. Hydroxide ions soak up hydrogen ions. So we call this a base. We call anything a base if its primary function in a solution is to soak up hydrogen ions. Hydrochloric acid, which is a powerful acid, when it dissolves in water, actually gives lots of extra hydrogen ion. We call an acid anything that adds hydrogen ion into a solution. When we measure the acidity or basicity of a solution, we use a scale called the pH scale. What I want to point out about pH, capital H here, that stands for hydrogen. It is telling us that this is a scale of how much hydrogen is there. The scale runs from 0 to 14, but I wanted you to note that the scale is kind of upside down. The lower the number, actually the higher the amount of acid. So you see here hydrochloric acid, which is about the strongest acid we can think of, has a pH close to 0. That's a lower number, meaning a higher acidity. Our stomach acid is pretty impressive. It has a pH of about 1. Each number that we see here, 0, 1, 2, is actually a tenfold decrease in acidity. So a solution going from a pH of 1 to a pH of 2 means it's tenfold less acidic. Okay, a couple of other things to point out here. A pH of exactly 7, which is what pure water is, means that the amount of hydrogen, the amount of hydroxide ion, OH minus, are exactly the same. We would call this a neutral solution. Anything with a pH number higher than 7, we would call a base. So actually less hydrogen ion than pure water. Notice human blood is just a little bit basic. It's just a little bit higher than 7, meaning that it is technically considered a very weak base. Living things have a very, very narrow range of pH in which they can survive. For example, our pH in our blood is about 7.4. If our pH changes much, like let's say our pH drops to 7.0 or it rises to 8, we can easily go into a coma or easily die. So living things spend a lot of effort making substances called buffers. Buffers are like chemical sponges that soak up extra acid or extra base to try to keep the pH of a solution fairly consistent. We have buffers in our bloodstream that soak up extra acid, or in some cases soak up extra base, to try to keep our pH 7.4. That concludes the most important elements of Chapter 2 as it relates to general biology.